And so today we want to consider elasticity. This is one of the very important topic in physics. And so what then is elasticity? You see, elasticity is the ability of a material to regain its original shape and size after being distorted by an external force. Actually, every material is elastic, but the elasticity of every material differs. But at the basic level, we take elastic material to commonly mean a material that stretches when we try to stretch the material. So an elastic material will tend to regain its original shape after it has been stretched, or you say after it has been distorted by an external force. You see? So, you see, the law that governs the extension of an elastic material and the force that extends it, or the load that extends it, was stated by Robert Hooke. What then is the law? You see, Hooke's law states that provided that the elastic limit of an elastic material is not exceeded, that the extension of an elastic material is directly proportional to the force or load. You see, mathematically, this simply means that force is directly proportional to the extension of the elastic material. But understand that on one condition, the elastic limit of the material is not exceeded. We will come to that as we look at what elastic limit means and other important points along the line of the graph of force against extension. You see, we can say F is equal to K times E. You see, here where F is the force or load and E is the elastic limit, or we call it stiffness. Some also call it elastic constant. Still means the same. Sorry, that is K, not E, sorry, K, the elastic limit or stiffness or elastic constant, and E is the extension. Is measured in meter, actually meter, meter. This is measured in Newton per meter, while the load is in Newton. So take note of that. Now let's illustrate and let's talk about what extension should mean. For instance, let's say I have an elastic material, let's say a spring. This way. Now, this is the unstretched length of the spring, always denoted with L naught. The unstretched length, meaning that it has not been distorted. Now, if a load is placed on it so that it stretches it, now this is what we call the L1. In this case, the extension becomes L1 minus L naught. Let's also assume that a bigger load is used to stretch this. Now this becomes L2. And now you can say that the extension here will be L2 minus L0. Extension is always with respect to the initial length or the unstretched length. So you need to take note of this. Sometimes we call this E1, sometimes we call this E2, denoting that this is what the load here causes, the second load, and what the first load causes actually. So this is the first load. Let me not call it L1, L2, so we don't confuse things. But this is load, the first load. The first load causes the first extension, load 1, and this is called load 2. Load 2 causes the second extension. So that's that about that. So this has to get your extension. Probably they give you the unstretched length of the spring, and then later, when being stretched, they give you the new length. So that's that about that. Example 1. A force of 0.8 Newton stretches an elastic material by 2 centimeters. Find the elastic constant of the spring. We are looking for the K. Now, first of all, we have to write out our given. The force is equal to 0.8 Newton. The extension is given as 2 cm divided by 100 actually. And this will be equal to, so that you can convert to meter. This is 0.02 meters. And now we have to get the K. So what we simply do here is to say F from our Hooke's law is equal to KE. And so our K will be equal to F over E. The force is equal to 0.8 Newton divided by the extension 0.02. So if we do this, we are going to have 40 Newton per meter. That's our K for this question, our elastic constant. Example 2. If a load of 1 kg stretches a cord by 1.2 cm, what is the force constant of the cord? Already for this question, we are given just the mass, 1 kg, and we are given the extension, but it stretches it by. The word by is used to denote extension, 1.2 cm. First and foremost, we have to go and get, this is a load given to us in mass, in kg. So how do I get the weight? Weight is mg. Now I have to convert your mass to force, because weight is a type of force. And that will be 1 times, our g is given as 10. So this is 10 Newton. And our extension in meter will be 1.2 divided by 100. And that will be 0.012 meters. And so we have to get K, just like the example 1. So we just need to say that since F is equal to KE, that K itself will be F over E. Our F is given as 10 divided by 0.012. So we have 10 divided by 0.012. And that's 833.3 Newton per meters. Example 3. The extension in a spring when 5 gram weight is hung on it was 0.5 cm. How do we write this? First of all, we are given the mass, 5 gram. We have to convert to kg actually, so divided by 1000. And that's 0.005 kg. And then from this, you have to get the weight, which is like the first force, F1. And that will be mg. That's the value for, that's how to get your weight. Your mass is 0.005 times g. We're not giving g, but take g as 10 meters per second square. And so that will be times 10. That will be 0.05 Newton. Now, again, the extension 1 is given as 0.56 centimeter divided by 100. That will be 0.0056 meters. Now, we are told that if Hooke's law is obeyed, what is the extension caused by a load of 20 gram? We are given a second mass. Let's call this the first mass. A second mass of 20 gram. So we have to convert to kg, which is 0.02 kg. Now, the second weight, which is our F2, is M2G, meaning the second mass times G. let's call this M1G. Our M2 is 0.02 times G, 10, and that will be 0.2 Newton. We have to get the E2. Now, how do we solve this? We simply do that F is equal to KE, and so we can say that K is equal to what? F over E. So we get the K first. That's one way to solve this question. So in this case now, we say, if I'm looking for K, since I have F1 and I have E1, I cannot do F2 over E2 because I don't have E2. But I can use F1 over E1. The K is constant. If you like use F1 E1 or F2 E2, you see the same thing. So our F1 is giving us 0.05 divided by E1, which is giving us 0.0056. So to get your K, actually, you can use F1 E1 or F2 E2. You can't use F1 E2 or F2 E1. No, it's not possible. Corresponding value of force to the corresponding extension. So let's get the K now. That will be 0.05 divided by 0.0056. This is 8.93 Newton per meter. Now, I can as well say that since F2 will also be equal to KE2, meaning that you can say Hooke's law, since Hooke's law is F equal to KE, you can say F1 should be equal to KE1 or F2 is equal to KE2. And so I am looking for the E2. Obviously, E2 will be equal to F2 over K. And so what is our F2? We are given our F2, which is gotten with from M to G, 0.2, divided by our K is gotten as 8.93. So the K you get from F1 E1 is still the same K you will use for, if you like, have another third force and third extension. It's still the same K you'll be using because the constant does not change. That's why it's called a constant. 0.2 divided by 8.93. This is giving us 0.0224 meters. You can choose to convert to centimeter. That's multiplying by 100. So our E2 can now be 2.24 centimeter. And that's because our question was given in, extension is given in centimeter. So that's that for this question. Example 4, an elastic material has a length of 35 cm when a load of 40 Newton is hung on it. You see, right here, we are given the first force, 40 Newton, and the first length, L1, 36 centimeter, which you can convert to meter, and that will be 0.36 meter. Again, we are also told that the under length of 45 cm when a load F2 of 60 Newton is hung on it, we have to find the original length of the spring or the string, which is also the unstretched length of the string. Very, very simple, but we know that F is equal to KE, and our K is equal to F over E, which can be F1 over E1, or you say F2 over E2. But our E1 is gotten with L1 minus L0, and your E2 should be gotten by L2 minus L0. We have both L1 and L2, but we don't have L0. So imputing that into this, let's equate these two. Since F1 over E1 is same as F2 over E2, which will give you your K. Our F1 over our E1 should be gotten with should be replaced with L1 minus L0. And our E2 should be replaced with L2 minus L0. What's our F1? That is 40 over L1 minus, so we have our L1. L1 is 0.36 minus L0 is equal to, our F2 is 60 over L2 is giving us 0.45 minus L0. And so this is it now. We can now cross multiply. Well, to make the solving easy, I can first of all, before cross multiplying, cancel out zeros from here. I will now have 4 over this and 6 over this. Or without cancelling, you can cross multiply. You will still get the same answer, just to be fast actually. And so this will be, cross multiplying here, this will be 4 times 0.45 minus L0 is equal to 6 times 0.36 minus L0. Now if we multiply this, 0.45 times 4, that will give us 1.8 minus 4L0 is equal to 0.36 times 6, 2.16 minus 6L0. So bringing this here, I'm taking this here. If I bring this here, I'll get 6L0 minus 4L0 is equal to this one coming here, 2.16 minus 1.8. This will give us 2L0 is equal to, if I subtract this, that is 2.16 minus 1.8. That's 0.36. So dividing both sides by 2, L0 becomes 0.18 meter. That's the stretched length of the spring. We can leave that in centimeter because that's what the lengths were initially given. And that will be L0 is equal to 18 times 100 centimeter. So that's the stretched length, original length of the spring. So this is the graph of load against extension. There are several points here, very, very important. This is the origin O. This is the point P, known as proportionality limit. E is the elastic limit. Y is the yield point, and B is the breaking point. For some materials, the proportionality limit and the elastic limit are relatively close and considered to be just a point. While some material, there's a little bit space between the yield point and the elastic limit. So from O to E is the elastic region, and so at this region the material is still elastic. And from Y to B is the plastic region. The material has yielded all its elasticity and has become plastic. Now, what then is proportionality limit? It is the limit of force beyond which Hooke's law won't be obeyed. And then the elastic limit is the limit of force beyond which the elastic material won't regain its original shape, even after the distorting force has been removed. Now, let's explain this graph of load against extension. You see, the graph is actually a straight line from point O to point P, which shows that from point O to point P, Hooke's law is obeyed and the material still regains its original shape. But from point P to point E, Hooke's law is no longer obeyed, but the material will still regain its original shape. If the applied force stretches the material beyond point E, which is the elastic limit, the material will not regain its original shape, but still have some elasticity in it up to point Y. Now, if we apply a force that stretches the material beyond Y, the material becomes purely a plastic and is no longer elastic. And from point Y till point B, if you keep applying force till the material gets to point B, the material tends to snap, or you say it cuts. And so that's what actually happens here. So that's that about this graph.